That's where we are. Okay, so 6.1 talks about. Oh, I can turn that off. It's getting a bit crazy.
Keep the volume on.
You want the volume on?
Yeah, it makes it more interesting.
Okay, well, I want to make it interesting. All right. So, polygons. Okay, we talked about polygons, and we kind of want to know what the definitions are, how to classify them, etc., etc. Introductory, basic stuff. Okay, so first of all, polygon. You probably had looked at this maybe online, maybe you looked in your book a little bit. Polygon is of course, it's a plane figure. What's that mean if we talk about plane figures in geometry? 2D. Yeah, we can draw it on a plane, right? Plane figure that meets the following criteria. It's formed by 3 or more. You have to have at least 3. 3 or more segments called sides. So these are all going to be the sides, such that no 2 sides with a common endpoint are collinear. In other words, that one may seem a little bit odd. What that means is it wouldn't make sense for me to have a point there, would it? What does it do? Right? I've got this straight segment already. By putting a vertex in the middle, it doesn't accomplish anything, right? So we can't do that. Wouldn't make sense to do that. We're only going to have vertices where the sides are at some angle to one another, not if they're collinear. What else? Each side intersects exactly 2 other sides, no more, no less. It has to intersect exactly 2. So if you look at each of these sides where they meet at a vertex, the vertex always connects to exactly 2 sides. Okay? We already know what a vertex is. We're talking about triangles. We know a vertex is where the sides meet. Plural is vertices. We know that too. And how do we name a polygon? With triangles, we always made the little triangle symbol, or in Moodle maybe we wrote the word triangle. But for polygons that are bigger than triangles, we don't bother making a shape because the shape can change. And so what we do is we just list the vertices in consecutive order. Okay, what do I mean by consecutive order? If I'm going to list the vertices consecutively. Mr. Banks, come on up, you got mail. Actually, what does it mean if we have to list the vertices consecutively? Okay, either clockwise or counterclockwise. It doesn't matter, but we got to list them in the order that we would run into them if we were to walk around the outside of the polygon, or half of it. Right? We couldn't say, like we could say, for example, P, Q, R, S, T would be fine. Or we could say T, P, Q, R, S. That'd be fine. What I can't do is I can't skip around. I can't say T, Q, P, R, S. It has to go in order, right? Okay, so got that. Yeah, go ahead. Okay, so what about these figures right here? We want to decide which of these are polygons, which aren't. How about A? You buy it? Okay, seems okay. Straight segments, yeah, makes sense. Looks like all of the vertices intersect exactly 2 sides. Looks good. How about B? Yeah. Check. B looks good. How about C? Yeah. Okay. How about D? No. Oh, what's wrong with D? Oh, okay, that's not a segment, is it? Got some arc there. That's not going to work. D's no good. How about E? Obviously no good. How come? Okay, it's not closed. Good. And so, in other words, this vertex out here, how many sides is it touching? Only 1. That can't work. So E's no good. How about F? No. What's wrong with F?
It's touching 3 sides.
Okay, yeah, look. If we look at this intersection right here, that vertex in the middle, how many sides is that touching? 4. No good. Can't do that. Can only touch 2. Good. Okay, so we got it. Okay. So far, so good. Okay, and so this I don't think is as big a deal as the book makes it out to be, honestly. It's good to know, be familiar with these names, but you're not going to use them that often. Some of the really common ones maybe, but a lot of the weird ones you won't. Polygons are named by the number of sides. It says memorize, but I don't. Be familiar with them. 3 sides, obviously we dealt with that a bunch. That's a triangle. 4 sides, quadrilateral. Quad meaning 4, right? And then we start getting into the more standardized names. 5 sides is a pentagon because we know penta means 5. Hexa means 6, so 6 would be hexagon. Hepta means 7. And the way I remember that is like a heptathlon is when you have 7 competitions in track, 7 events. 8's obviously an octagon. 9's one you may not have heard. A nonagon is 9. 10's a decagon. 12's a dodecagon. And after that, I don't remember. Seriously, I don't remember. Because here's why I don't remember. Because you don't need to. Whenever you start dealing with polygons that are bigger than, octagons, let's say, you can just call it an n-gon. So if I have a 21-sided figure, I have no idea what a 21-sided polygon is called. I can't remember that a bit. But I would call it a 21-gon, and that's fine. Just put the number of sides followed by gon. So it look like this. 21-sided polygon. It's a 21-gon, and that's fine. Tells you exactly what it is. Okay? There's your shortcut. Okay, convex or concave. Now, a polygon is convex if no line, if I extend all of the sides, if the extensions of the sides don't pass through the interior. Okay? Now, on a concave, or non-convex, whatever you want to call it, that's not what happens. If I extend, notice what happens here if I extend all of the sides. Well, I've got this one right here or this one right here. If I extend these sides, the lines pass through the interior of the polygon. So that means it's concave or non-convex. There's another way to think about this, just kind of visually. Concave, what does it mean for something to be concave? It means it's dented inward, right? It makes a cave, literally. So this polygon has been dented inward and it's created this little cavity or this little cave. And so you can see that it's just by looking at it that it's concave. So it's very visual. You don't even have to use that definition, although you can. Okay, so what about this top one? Concave or convex? Concave, yeah, clearly. This one? It's not concave, right? It's not dented in any place, so it must be convex. All right. Okay, so a couple other things. Polygon is equilateral. We know what that is. We've dealt with triangles. Equilateral just means literally same side. All the sides are congruent. Equiangular, we know what that means. Same angles. And then if both of those are happening simultaneously, if a polygon is both equilateral and equiangular, we say that it is a regular polygon. Okay? So tell me here then. Which of these are equiangular, which are equilateral, and which are both, which are regular? How about this top one? What's that guy? Okay, equilateral. How do you know? Yeah, it tells us, doesn't it? It tells us by looking at those congruent statements, all of the sides they all get one congruence mark, so they're all congruent to each other. So that one is equilateral. Okay? But not equiangular, right? How about this one here? Say it again. Equiangular, yeah, right? Makes sense because all the angles are right angles, but the sides are not congruent. So that guy is definitely equiangular, but not equilateral, so it's not regular. How about this one? Equilateral, not equiangular. Good. Okay, and then finally this one right here. Regular, both. All the angles are congruent, all the sides are congruent, so it's both. Okay. Okay, here's what I want to look at a little bit. we can come up with a cool pattern that's going to allow us to do something with bigger polygons that we'll use later. Not so much this section, but later on we will. What are the diagonals? Okay, the diagonals of a polygon are segments that join two non-consecutive vertices, right? So we're going to skip. We're going to skip at least one vertex. So if we're looking at the diagonals of point Q, QR wouldn't qualify. That's a side, right? Sides and diagonals can't be the same thing. They're different. QR is a side, QP is a side. But as soon as I skip through R or I skip through P and connect Q to one of the other vertices, those form diagonals, right? So this has exactly two diagonals. Okay, what I want to do now is I want to take a quick look at these shapes. Okay, I've got a sample of 5 different polygons here. Let's make a little table out of this. We're going to track the number of sides and we'll call that in. Okay. Let's find the number of triangles that can be divided out by the diagonals. And what I mean by that is, for example, let's just take the first 2 together and you can tell me the answers to the rest. This first one up here, how many sides has it got? 3. Are there any diagonals in a triangle? Can't be, can there? Because if I take, for example, this vertex up here, the only other vertices are ones that are connected by sides. There is no non-consecutive vertex because all the vertices are next to each other. They're all just one away from each other, right? So this one has exactly one triangle we can divide that into. Now let's look at the next one. What about this guy? Let's say we start up here in this corner. How many sides? 4. How many triangles can I divide that into? 2, okay. Okay. How many diagonals are there? 1, okay, and there's 2 triangles. How many diagonals in the first one? 0. How many triangles? Do you think you can maybe suggest a pattern there? If I count the number of diagonals, how many triangles am I going to get relative to that? 0 diagonals gave me 1 triangle. 1 diagonal gave me 2 triangles. What do you think? Let's try another one. How many sides on this guy here? We said 2. So we'll start up here. 5 sides. Good. How many diagonals? 2. There. There. Right? So 2 diagonals. How many triangles? So what do you think the pattern is then? If I count the number of diagonals, how many triangles? 1 more than that, yeah. So the number of diagonals plus 1. There's one pattern you see. Okay. So we have 5 sides, 3 triangles. Now what if we want to add up all the interior angles? If I add up all the interior angles in a triangle, what's that add up to? 180, yeah, good. So we get 180 degrees. What's going to happen here if I have 2 triangles? How many? What's the total of all the interior angles they're going to be then? It's going to be good. It's going to be here. I had my 180. Here I get my 180 and 180. So 2 times 180 is going to give me 360. How about here? What do you think? 180, 180, 180. 180 times 3, right? The number of triangles I get allows me to add up the total of all the interior angles of that shape. triangles, we know, always have 180 degrees. It turns out quadrilaterals can always be divided into two triangles, and so they always have 360 degrees of shared interior angle. So the sum of the interior angles is always 360. For pentagons, it's going to be 540. And if we keep going with this, what do we got? 1, 2, 3, 4, 5, 6 sides. How many diagonals? 2, 3. So we got 3 diagonals, 4 triangles. So how much angle then? 4 triangles, so 4 times 180, right? So it's same as 2 times 360. We could keep going with that, but let me ask you this. If I don't specify, what if I know I have a polygon with n sides? How many triangles do you suppose it's going to have? What's my pattern? -2, right? That's what happened every time. So the number of triangles I can cut a polygon with n sides into is going to be n-2. And so what's my formula going to be for the sum of all the interior angles then? What did I do to get each of these numbers? Yeah, I just multiplied the number of triangles times 180, right? So then if I want to come up with a formula here, isn't it just going to be n-2, whatever that is, times 180 degrees? How about that? We got a formula. Now we can always, even if we had a huge polygon, if it had 39 sides, we could predict what the sum of all the interior angles would be by just using this formula. What if it did have 39 sides? How could I calculate the sum of its interior angles? Yeah, so 37 times 180, that's it. Okay. Oops. Okay, so then we can do easy stuff like this, can't we? If we want to solve for the measures of the, not that, those all add up to 360, we talked about that, but we could do something like this, couldn't we? We could solve for the measure of angle Q and the measure of angle R here by just finding out what x is and plugging that value of x back in. The equation we'll use would just be, because it's a quadrilateral, it's got 4 sides, we know that the interior angles all add up to 360, and so there's my simple equation. X plus 2x plus 70 plus 80 is 360. We can just solve that. No big deal. If we solve that, we just add like terms, subtract 150, divide by 3. If x is 70, then angle Q is 70. Angle R is 2 times 70, so it'd be 140, right? Got it. Okay, so that's 6-1, no big deal. No big deal at all. We got lots of sound effects here for you. Oh boy. Okay. So, parallelograms. Okay, real quick. We all kind of probably know what parallelograms are. You've heard about them before. We know what they look like. The definition is real simple. Any quadrilateral that has 2 pairs of opposite parallel sides, that's a parallelogram. So these 2 sides have to be parallel to each other, and those 2 sides have to be parallel to each other. That's what it means to be a parallelogram. We have some properties of parallelograms, a bunch of theorems and postulates, and I don't care if we remember which one is which. We'll just call them the properties of parallelograms that come with that. If we know that a quadrilateral is a parallelogram, then a bunch of things are true. For one thing, if it's a parallelogram, then both pairs of opposite sides have to be congruent, always. That's one property of a parallelogram. We also know that, so we would know in this case that PQ has to be congruent to RS. That should be, okay, PQ and RS, and then QR is congruent to PS. Okay, also, not only are opposite sides congruent, opposite angles are congruent. Okay, so angle Q has got to be congruent to angle S. Angle R has to be congruent to angle P, right? That's always true. That's true. Not only is that true, we know that consecutive angles are always supplementary. So they're always going to add up to 180 degrees. So any two I pick, measure of P plus the measure of S would be 180. Measure of P plus the measure of Q, because they're consecutive, they're next to each other, they have to add up to 180. Any combination of two that are next to each other. Yeah. You like that? If a quadrilateral is a parallelogram, then also something else we get, and this one's a little bit harder to see maybe. If we draw in both diagonals in the quadrilateral, we know that they're going to bisect each other. Now, this is a word that, as of about a week ago, not everybody totally understood. Let's see if we got it here. What does it mean to bisect anything in geometry? Cut into two, almost, that's a big part of it, but there's something more specific. Cut into two equal halves, or congruent halves, right? So anytime something is bisected, it's cut exactly in half. So if these two segments are bisecting each other by cutting each other at point M, then I know that PM has to be congruent to RM, right? Because PR has been bisected. It's been cut into two congruent halves. Same thing is true for segment QS. It's cut into two congruent pieces, right? So whatever the midpoint is, the place where this thing has been bisected, that's what's going to form these segments that are congruent. It's not just cutting in two. They got to be congruent. It's bisected. All right, so what about this one then? Using those properties of a parallelogram, can you tell me, just real quick by looking up here, don't say anything yet, let everyone have a chance, but what would be the length of segment JH, or side JH? Think what? So we know that polygon FGHJ is a parallelogram. And we can see that because both pairs of opposite sides are parallel, right? So what do you think? What's the length of JH going to be? 5. Opposite same 5, yeah. And how come? Yeah, opposite sides are congruent, right? So we know this has to be true. So if that's 5, that's 5. Okay, what about JK? What about JK? What's that have to be? 3. Now, do you understand what these numbers mean? That little 3 right there, what is that 3 referring to? You might think, is it this segment or is it the whole thing? Well, anytime a number is next to a segment, you have to assume it's specifically referring to just that segment. So that 3 goes with that part right there, right? And we know that being as these are the diagonals, they have to bisect each other. And so those two segments have to be congruent, right? So this has to be 3, okay? Okay. Find the angle measure of angle R. What's it going to be? 70. Got to be 70. And what's our reason for that? In a parallelogram, what's one property of parallelograms we have that's going to apply here? How do we know that's 70? Okay, opposite angles are congruent. Good, so that's got to be 70. Now, what about Q? What's it going to be? 110. How do you know that? Yeah, okay, consecutive angles have to add up to 180. So if that's 70, that has to be 110, right, in order to make 180. Good. Okay. All right. Got that. Okay, what about this guy here? There we go. Okay, what about this one? If I want to solve for x, what could I do there? What's the easiest equation I could probably come up with? Got it. I've got an x in my picture, so I have to be able to come up with some relationship that's going to give me an equation. What do you think?
3x plus 120.
Yeah, there you go. 3x plus 120. equals 180. Subtract 120, divide by 3, got it. X is 20, no big deal. Okay? Okay, let's look at a little proof. Here's the picture we're given. We're told that polygon A, B, C, D. So this guy up here at the top is a polygon, and A, E, F, G is a polygon. We're supposed to, or excuse me, are parallelograms. So telling us those are parallelograms. We're supposed to somehow prove that angle 1 and angle 3 are congruent. What do you think? Any suggestions how we could do that? It's a real short one. I'll give you that hint. It's a short proof. We don't need many steps to this at all. Got to prove that angles 1 and 3 are congruent. What do you think? What do we got? Suggestions. What do you think? Delaney?
3 and 2 are opposite, and then 2 and 1 are opposite.
Okay, there's something. So we see here that angle 1 has to be congruent to angle 2. And our reason for that is that they're opposite angles, right? If we have a parallelogram, we know opposite angles are congruent. So let's draw in these congruences. So that's true, right? And 2 and 3 are also congruent, right? Okay. And so opposite angles congruent. And then that's all we need, isn't it? Now we should be able to say if I know that 1's congruent to 2 and 2 is congruent to 3, then I should be able to say that 1's congruent to 3. Now what's my reason for that? Do you remember that one? It's one of those it's on the first page of that handout that we were using earlier. What is that one? If A is congruent to B and B is congruent to C, then we ought to be able to say that A is congruent to C. What was that property? Do you remember? It's like we're transferring the congruence from 1 to 2 to 3. Transitive. There we go. Transitive property. Okay, so transitive property of congruence. Good. So that gets us there. Okay, that was a pretty easy one. Let's try maybe one that's just a little bit harder.
Oh.
Okay. How about this guy? Okay, so let's prove one of the properties of parallelograms. Okay, we're going to prove that side AB. If we have a parallelogram, let's prove that opposite sides are congruent to each other. Okay. This is another one. I want to go through this one because here's another second example we've looked at where we're actually going to add something that wasn't originally there. Right. I'll tell you what. I'll just uncover the steps. And we'll try to maybe come up with the reasons. So we know this is given to us. They tell us that this is a parallelogram. So that's given information. That's easy. Okay, now what about this other part? We can add this segment BD. We're free to do that. That's okay. We could say it's given, in fact. Really what you probably would say is by construction. But it's fine for us to just say it's given. We can make that thing. There's no reason we couldn't. We can always connect two vertices and make a segment. Okay, so if we do that, how about this next step? How do we know that side AB is parallel to side CD and side AD is parallel to side BC? With just the stuff that we're given, how do we know that? They told us something there that implied that those sides have to be parallel to each other. What is it? It's a parallelogram. Exactly. It's a parallelogram. And if it's a parallelogram, that's the meaning of a parallelogram, right? The definition of a parallelogram is a quadrilateral where the opposite sides are parallel to each other. So that's our reason. It's just the definition of parallelogram. Okay, and let's mark that in. Okay, so we know then that that's true and that's true. All the information we'll put on our drawing. Okay, how do we know this then? Here now, this takes us back a ways. how do we know that angle ABD is congruent to angle CDB, for example? So ABD, that's that one right there, right? And CDB is this guy down here. So this angle and that angle, how do I know those are congruent? Of course, almost. Alternate interior, good. If I extend these sides up here, look what happens. If I extend side AB and I extend side CD, and then this becomes a transversal, that looks familiar, doesn't it? If two parallel lines are cut by a transversal, those would be alternate interior angles, right? And they have to be congruent. Make sense? Okay, and by the same token, I could do the same thing. Go back a little bit. If I extend these sides and make this the transversal, then doesn't that mean that now these are the alternate interior angles? These guys in here, right? DBC and ADB, these other angles there and there. Right? And so I should be able to get both of those for the same reason, right? Because I've got a parallelogram. I've got these parallel lines being cut by that transversal that's really just the diagonal. Okay, so I can say both of these things. And my reason is just, as you told me, alternate interior angles. Okay. Now, that gives us, that's pretty good. Now, look, I've got in these two triangles, if I'm dividing this into two triangles, in the top one and the bottom one, I've got two congruence marks in each. Right? How many do I need to prove the triangles are congruent? 3. So what's my other one going to be? What's the other one? I've got these two, both of those angles in the top triangle are congruent to both of those angles in the bottom ones. What's the other congruence I get here for free? No, not necessarily, because I don't know it's a parallelogram yet. That's what I'm trying to, well, actually, hang on. Yeah, I pretend I don't have the properties of parallelogram. Sorry, we do know it's a parallelogram. But we're trying to prove the properties of parallelograms. So let's assume that we don't know any of the parallelogram tricks yet. Okay, you were right. I'm cutting you off. I'm not using that one. What's another one we can get? Yeah, DB, right? It's a shared side. DB should be congruent to itself. By what property? Reflexive property. Okay, and now we got our 3 congruence marks in each triangle. What's the pattern going to be? Yeah, angle, side angle, or angle, side angle. Both triangles. So I know that the two triangles, the top and the bottom one, are congruent. Right? By angle, side angle. And then now we get down to the final step. How can I show that side AB is congruent to side CD, for example, if I know the two triangles are congruent? Yeah, that's got to be that CPCTC one, right? Corresponding parts of congruent triangles have to be congruent. Those are the sides. If I pick up the bottom triangle and flip it around and overlap it with the top one, wouldn't you agree that AB is going to correspond to CD? So they have to be congruent. Okay. Final step. That's true, and that's true by CPCTC. Okay? Make sense? All right. Okay. Good stuff. Just tell me that. All right. Just about. Okay, I gotta take a roll. I'll let you guys. That was a lot of stuff. I'll let you just relax for a second. How about?